I need to introduce you Professor Eremeyev. I met him several years ago, and my consideration about Russian School of Mathematics and Mechanics increased after having met him. As we are a little bit late, I will stop telling good things about him, another negative side effect, and I leave him the microphone. Thanks, Victor, and sorry.
Okay, thank you very much for the nice invitation, short invitation. In this case it will be more effective, let's say. So let us start our lecture, which is last lecture, plenary lecture for this nice conference, and I would like to say good words to organizers because they did very effective work about this conference. Organization of conference is not so easy. It's not so easy to manage all problems, including the problems not scientific, completely non-scientific problems. So I thank Professor Francesca, Professor Marco Amabili. I also thank the, let's say, staff who manage this, Daria Scerato, Ivan Giorgio, Emilio Barchesi, and many others who serve us to do it. And now I'm switching to surface elasticity, the topic of my lecture. And recently, yesterday, Professor Reddy mentioned different generalized theories of continua, such as like micromorphic, micropolar, strain gradient, etc. Let me note that there is also another extension of classical elasticity into some kind of generalized media. It's called surface elasticity. So I will present some results about surface elasticity, and with some applications. Of course, there are many applications, so I chosen some which I like. Okay. Let's go. We have some short introduction with nice pictures, the basic relations of elasticity with surface stresses, and we consider it two, let's say, applications. First application relates to influence of surface stresses, surface elastic properties of material on the apparent or effective material properties like stiffness, bending, stiffness, etc. In this case, presence of surface stresses changes material properties, and on the other hand, there are also some new phenomena which is just thanks to these surface stresses, and we consider some kind of new phenomena related to surface waves. So-called anti-plane surface waves, which does not exist in the case of classical elasticity, but exist in this case. And some of results will be related to some kind of materials with so-called non-perfect surfaces, like deformed or regular surfaces based on, let's say, some arrays or nanoforests, and some conclusions and so on. Okay, I will, since lunchtime is approaching and I don't delay this last lunch for this conference, I will skip. I just to say that, okay, development in nanotechnologies, we have some kind of new phenomena, and such like size effect, which is we discuss a bit later. And so we need somehow to improve the classical elasticity to capture the size effect and other things which we have at nanoscale. So the aim of the lecture is to discuss some effective constitutive equations for surface stresses, taking into account some structure of surfaces or surface coating, and to analyze the influence on this. Coming back to the history, let me say that the first rational, in some sense rational approach to surface phenomena was quite old. It was the works by Laplace and Young, who introduced the surface tension, so-called capillary fluids. And let's say almost 100 years ago, two another guys, van der Waals and Korteweg, they produced so-called unified gradient type models, which is known now like molecular capillarity theory. And the basic difference between these theories is just like that. Laplace-Young suggests sharp interface. We have the surface with additional surface energy, whereas van der Waals and Korteweg, they propose some interfacial layer. In this case, surface energy relates to the, let's say, average through the interfacial layer, energy of this interfacial layer. Okay, so speaking about surface elasticity, it was also nice, it should be mentioned the works by Gibbs, Josiah Wheeler Gibbs, who introduced surface tension for crystals and solids, let's say in general, and for most applicable theories, it was theories by Gert and Murdoch, and then this theory was extended by Steigman and Ogden to considering the bending stiffness. And there are many things related to surface, even let's say finite element realization was done by group by Ali Javili and Paul Steinman. And there are many reviews in the field considering different, let's say, sides of this phenomena. And this nice picture shows us, here it's more nice than there, that typical capillarity we met maybe not all the day, but it's very often. So the shape of these drops is completely determined by the surface tension of water and these leaves. And so it is just typical capillary phenomena, and it could be useful by animals and also by let's say science. And where is the surface tension, surface energies plays a role? It's typical examples like phase transition, problem of nucleation, fracture mechanics, for example, Griffith's energy and energy line tension, energy in dislocation core. Of course, surface phenomena is quite important for porous materials, for any materials where we have, let's say, very developed surface and number of, let's say, material particles lying near surface is much comparable with the particles in the bulk, and other properties like surface wave, surface diffusion, for example, capillarity. Surface tension is responsible for so-called capillary waves in hydrodynamics. Let us come to some experimental observation about size effect. You can see that forecast, let's say, macroscopic behavior of this material, zinc oxide, which is quite popular for blue laser techniques, and properties measured with respect to the diameter of this specimen. And you see these red dots in some approximation fitting curve, which quite different from this line. So it means that in this case we have stiffening, and this stiffening means that we should say who is responsible for such stiffening, what is the phenomena behind that. Another experimental data from different papers, we see similar behavior. It's quite different from, let's say, line. And also some kind of molecular dynamic calculation also shows the difference for different crystalline planes of some materials. You have some size effects, and the people in the group by Professor Bhushan Karihalu, Hulin Doan, Wang, and many people, they considered, let's say, such properties like porous materials. They calculated effective dependence on size of pores, which is not behaves quite different from the bulk behavior. And finally, this group suggested some kind of scaling law, which nothing else like Fourier series. We see if you have some macroscopic property which depends for infinity, it means for the classical bulk behavior, and we have some size specimen of size L, we have characteristic size which looks like that. We have some intrinsic, some kind of characteristic lengths and some parameters. And exotic, in some sense exotic result, temperature of melting of nanoparticles looks like that. We have exact formula for this. Here I can refer to works by Franz Dieter Fischer for this case. And so coming back to our theory of surface stresses. Here we have surface stresses. It's a common, it's clear for everybody here. Surface is also clear about what we have in reality. We have in reality such perfect and non-perfect surface. Today we already hear it in this room. It was a non-perfect contact. It's in this conference it was several lectures about perfect and non-perfect contacts. And what we have for perfect contacts, it's example of perfect material surface, which is a mathematical surface, just a plane. It's a zinc oxide, because for these materials is quite important the property of this specimen, because it's a working agent in blue lasers, blue diodes. So it's just monoatomic plane. So you can see crystal, you can see these nanotubes, they are quite perfect, so it is mathematically almost planes, so it's prism. And examples of non-perfect surface is much more interesting, because you can see such kind of nanoforest of these perfect crystals of zinc oxide with magnification from, let's say, transparent. It looks not transparent, but in reality it looks like transparent film, which we became to such kind of, let's say, chaotic organization of crystals. Another modification, so-called black silicon, some enhancement surface, putting some elements periodic drops to absorb more energy. Vanta black material, which is one of the best in sense of absorbing of light. So-called self-cleaning polymer coatings, which is quite, for me, for example, having these glasses, I must clean it all the day, a few times per day, so it's much better to have something self-clean that somebody else do it. But okay. And this, you can see the shape of classical water drop on the classical surface and water drop on this, let's say, self-cleaning surface, which is hydrophobic, highly hydrophobic material, which is almost like a ball. And for example, such coatings, people suggest to use such coatings for making clean windows, to avoid some very expensive procedure of cleaning of windows for very high buildings, because it should be done, but nevertheless it costs money. And then they propose to use some such kind of coatings which looks with magnification very like foam-like material. Another kind of its fiber arrays for polyacrylate. It could be grown in chaotic way, it depends on length of this, or just ordered nanoarrays. You can see difference. Recently invited also some enhancement of the surface, so-called hyperbolic metasurfaces, which looks like, from mechanical point of view, it looks like ribs or beams or bars attached to the surface. It looks like another example. The scheme is given here. You have some surface with the ribs, and this photo demonstrates real object of such a kind. So we have different kind of surfaces, and phenomena which we observed. So we try to somehow introduce something which should capture such behavior. Okay, now we switch to less interesting topic, because we have many formulas here and some kind. Okay, so we consider it elastic body with surface stresses. Green means surface stresses is present here. And what we have? We have traction, and traction consists here in two parts. It's a typical external forces acting on this surface plus divergence, surface divergence of surface stress tensor. Surface stress tensor S is present here on this and other typical equations we have. The basic equations of surface elasticity, first in some rational framework, was proposed by Gerten and Murdoch quite a lot of time ago, and that time it looks like a mathematical exercise, very nicely written paper. And after, let's say, some time, its paper became very popular for people working with nanotechnologies. We have typical Lagrangian equation, equilibrium equation in the bulk with classical boundary condition. And what we have additional, traction conditions where we have the surface stress tensor, and this is just a generalization of known famous Laplacian equation in the case of surface elasticity. Okay, what we have here? We have here additional constitutive equations for the surface. So you have the surface energy and surface stress tensor, it should relate to surface. You have surface gradient of deformation. Or you can use some kind of more general equations, which is, for example, the second generalization was proposed by Steigman and Ogden, who considered the bending stiffness of these elements. There are many others, and here it should be Professor Luria who proposed another modifications of this theory to capture another phenomena. So first keystone of surface elasticity is additional constitutive equation on the surface, and second is a compatibility condition on the surface. So we have something vectors kinematics in the bulk, and we can simply assume that our position vectors of the surface is the limit of position vector is from the bulk. Of course, if you come back to this very complicated surfaces code, and you ask what do you mean by this vector? It should be some kind operator or something more general case. It's okay. It could be more general compatibility conditions. Okay, coming to constitutive equations. We have nonlinear elasticity. Here we have membrane theory here in the case of Gerten-Murdoch. Because they are independent, we can simply introduce residual stresses here. And for example, if we need to solve something simple, we have Hooke's law here, and we have some linearized Gerten-Murdoch theory when we have the initial surface stresses here, and we have strains here, and here surface strains, etc., etc., etc. How to measure these additional parameters? Additional parameters, there are straightforward calculations, like this atom force microscopy. You have nanobeams, you put your indenter here and measure the bending stiffness of this beam and consider beams of different diameters, and using size effect you can estimate this material parameters. There are some theoretical estimation for these parameters which looks like that. If you consider three-layered plate, you consider bending or tension of this, you have relation between, for example, shear modulus within the Gerten-Murdoch theory and limit of this factor, where mu f is just a shear modulus of this thin surface layer. So to illustrate the idea, we can consider tension of porous rod. It's just one-dimensional problem. In the case of classical elasticity, it's quite easy. We have the apparent effective stiffness Young modulus, which depends on the porosity, and nothing else is given here. But if you consider the same porosity but different number of pores, in this case surface stresses play a role. And what we have, if you do some, let's say, typical technique, we can obtain some formula within surface stresses. We also compare with typical mechanics of composites, like in book of Christensen. It's classic, nothing else. If we combine it, we have some kind of behavior, which n here is a number of pores for given porosity. When you consider some graphs, you can see some graphs for different formulas, and you see that now effective stiffness of the rod depends on the number of pores, and we can see that in some sense this dependence captures this size effect, because you have now effective Young modulus depends on the radius of the specimen, radius of our specimen, and we also have some characteristic lengths here. In the case, next step could be considered if we consider plates and shells, which is natural objects for nanomechanics, because we have nanofilms, nano-sized coatings, etc. And let me say that considering theory of plates and shells, I'm not sure that 12-parameter theory of shells was used for this, but others like Kirchhoff, Timoshenko type, Mindlin-Reisner type, von Karman type, and some exotic ones, let's say generalized theories of shells, was already extended for the case of surface stresses. So here we just present the idea. We consider the element of the shell, which we have again surface stress acting on the faces. We have some surface layers with different properties. We have the core inside, which models the bulk, and that's it. And the procedure could be quite simple. We integrate through the thickness this, let's say, structure, layered structure, and obtain the effective stress resultants and coupled stress tensors. And this reduction procedure looks like that. We consider this layered structure. We have something formally, even in nonlinear case, it looks like that. Our effective stress resultants looks like a sum of stress resultants inherited from the bulk and stress resultants inherited from these faces. In the case if you have multi-layered, this effect is more pronounced, of course. And coming to this formula, it is just integration through the thickness technique, which gives us the answer, how it depends, how our stress resultants will depend on this. I will skip this detail because it's just, in some say, complicated exercise in integration of equilibrium equations. It could be done also for motion equations, but it is more difficult, technically difficult. And finally, with kinematic assumptions like Mindlin-Reisner or Timoshenko type kinematic assumptions, we came to following constitutive equation for stress resultants and coupled stress tensors. Here, we have stretching, bending, shearing here. We have some coefficients which we obtained here. And finally, we obtained we can measure the bending stiffness and tangential stiffness of our shell, which looks like that. We have some ingredients here. The last, it's just inherited from Gerten-Murdoch model, this and that, and this is just coming from three-layered shell theory. And finally, if we introduce some kind of notations, we use typical bending stiffness, classical bending stiffness. You have the bending stiffness for three-layered plate or shell, and we have these additional ingredients, and we can see that we have similar but different dependence on thickness. And if you consider relations of this, you can see that we have also such kind of effects. So difference between our effective bending stiffness and bending stiffness without surface stresses looks like that. So you have, and if you use some real material parameters for aluminium taken from the paper by Duan, we have such kind of curve which looks like this size effect experimentally observed. So you can see that significant difference in bending stiffness when it's quite thin, in general, as it should be. We calculated other stiffness coefficients and some reference. We haven't time to discuss it. Now I switch to new phenomena. New phenomena consist, as I mentioned before, in classical elasticity we can consider it elastic half space. In this case, there are nothing which looks like antiplane surface wave. In this case, surface stresses, we have this. And in this case, we consider it what? We consider it our linearized Gertin model. So in the bulk we have classical elasticity with kinetic energy, with displacement, that's it. Linearized Gertin-Murdoch in simplest form looks like that. And what is crucial here, we have for Gertin-Murdoch model we have also kinetic surface kinetic energy. M is surface mass density. So it's typically came from, let's say, such materials. You have glass, for example, with deposited metal thin film. So this mass of this deposited metal is given. Is present here. Okay, so we can also consider it interface perfect and perfect. In the case imperfect interfaces, we have some kind of like spring model or more complicated model. This model was proposed by Luca Placidi, probably is here, and Rossi and Angelo Amadeo. And derivation and based on list action principle. So you have all ingredients, you have the function, we consider it variation, and finally we obtained, as should be, equilibrium equation of motion in the bulk. We have this equation in the surface, external surface, these more complicated conditions, let's say static or dynamic boundary conditions and imperfect interface. And here you can see, for example, if we consider this equation, from the point of view of the bulk, we have just boundary conditions. But from the point of view of surface, we have the motion equation. We have motion equation here, and here this term just is external force. Okay, and we consider it half space, we consider it this antiplane. Motion is quite simple because it reduced to one scalar function, and we have only wave equation in the bulk, so it's quite known and old equation. We consider it steady state. We do everything, so in the bulk we have such kind of representation of steady state solution. Ct is the speed of transverse shear wave in the bulk, and then we substitute it into the boundary conditions, which looks like that, and we find some kind of dispersion relations, which is presented here. And what we have? We have dependence of phase velocity, which looks like that. We have these dispersion curves presented here. Okay, in some sense it's quite similar to known old famous love waves when we consider it waves, shear waves in the half space with elastic layer. So we can, in the same way we consider it perfect and imperfect interface, we consider it interfacial waves. In this case, I skip details because I should speed up my lecture. We also obtain some kind, but in this case we have more rich behavior of waves, and so you have more interesting structure of dispersion relations. For perfect, it was for perfect interface. For imperfect interface we have more. We have some, okay. These additional cases, we have some cutting wave numbers here, so it's quite interesting and rich behavior. So just present of simplified version, within the simplified version of this Gertin-Murdoch model, we have additional new phenomenon, which is wave propagation, which was discussed from experimental point of view and mathematical point of view, for example, in the papers by Georgiotis, Panos. Okay, and what we have? Just if we try consider the same problem for gradient elasticity, we consider two-pin mingling gradient elasticity. Here we have additional ingredients. We have second deformation gradients inside. Here we have stiffness here. And just look how it looks here. We have stiffness tensors of 4th order and 6th order stiffness tensor. Even in energy, kinetic energy must be extended to the case of higher order terms with respect to velocity. And kappa is also 4th order tensor, which is given. And even in the case, okay, there is classical equilibrium motion equation for our strain gradient elasticity. We have stresses and hyperstresses here, and even for isotropic solids we have a number of parameters. We have, in addition to additional Lemma parameters, we have 5 elastic parameters and 3 parameters, inertia parameters. And in the case of antiplane waves, we have this equation, which looks like some kind of extension with boundary conditions. We have 2 boundary conditions because we have 4th order of equation. We do all this procedure for steady state solution. We obtain the solution, and finally we try to compare it with Gerten-Murdoch model. We use some parameters for strain gradient models and surface energy model, and if you ask me where are you taking it, it was some average and procedure by Giuseppe Rossi, who considered some, let's say, microstructured layer to make some calculations and average it to obtain some material parameters for strain gradient models. So we use it, and we have some kind quite similar behavior. So dispersion relation in general are the same. So curves, dispersion curves for phase velocity looks quite similar. They have the same limits. What is the difference is decaying rate. In the case of surface elasticity, decaying rate is these waves decay faster than for strain gradient elasticity. It's from mathematical point of view, it's clearer why, because here surface effects present on surface and here they present in boundary layer. And we consider it, for example, decaying layer with the depth, and you can see that it's different. For some wave numbers there is quite large difference in decaying layer. Recently, we can suggest some kind of extension of the model called strongly anisotropic surface elasticity. For this, it's most motivated by this hyperbolic metasurfaces with the bars. So we introduce this curvature of these bars is present here, and for such materials we can solve the same problem, but here we have some preferred direction along the bars and transfer to bars. So we can consider 2 modes. And what we have? We have 2 possible antiplane motions here. After some manipulation, we can consider that in this case surface hyperstresses are absent, while for the second mode the surface hyperstresses is present. So it's just shearing and bending modes in this case. And again we came to 2 wave equations with boundary conditions, and second boundary conditions has the derivatives up to 4th order. We calculate dispersion relations and show that our dispersion curve looks like that. This is a curve for Gerten-Murdoch model, GM, whereas for bending mode we have such behavior. So even when the bending stiffness goes to 0, initially we have identical identically like Gertin-Mordek, but nevertheless, after some threshold, we have difference in this. And probably it is because in this model we not take into account some rotationary inertia of beams which will produce some higher order term in surface energy. Again, coming back to ab initio principle, we can consider it some lattice versus continuum, and we consider it with my colleague Bazentlor Sharma. We consider it lattice, and to model surface elastic properties, we introduce a different material particles with a different mass. M, small m, is just a factor which shows difference between masses of particles in the bulk in here, and alpha is a factor which shows the difference of stiffness of these bonds, surface bonds, with respect to stiffness of bonds in the bulk. In this case, lattice dynamics, for lattice dynamics, we have finite difference equations, so you have ordinary differential equations. Here you see finite difference equations, and you have for the surface, and you have in the bulk, and for the surface is just this. We're also looking for the steady state solution, and we find some kind of implicit form of dispersion relations. And to capture the behavior, we first assume that our mass relates to parameters in the bulk, we try to somehow connect the stiffness of bonds with shear modulus and mass with the density. We obtain this form of dispersive relations, and we can see that they are quite similar. We have Gertin-Mordek model, we have some curve for infinite lattice, and we have in our lattice model you can similar behavior. Okay, but here we have discrete model, and let us consider what is going when A, which is a characteristic length of lattice cell, how it transform into when A comes to 0, what it will be in this case. In this case, we can suggest some scaling law, because if you do it in classical way, this surface rho will be neglected, and just this lattice transform into elastic half space where nothing such as surface antiplane wave exists. In this case, if we assume such scaling law, we can find some relations between surface moduli, in this case shear surface modulus and surface mass with respect to this, let's say, lattice parameters. In this case, you can see that when we have different values of A, we comes here and here. So we consider it through the prism of antiplane waves. We consider it surface phenomena. Hot science, I know. There is a very hot science, and thank you that you are sitting in this room. Okay, I will speed up better. Okay, we consider that this phenomena like antiplane surface waves can be described within many approaches, and there are some similarity, but there are also some differences in this. And now last step is just a few words about let's say complicated macrostructured surfaces. In his case, it could be very nice procedure, because we already see how it influences these parameters. We can consider it, let's say, 2D effective or apparent material properties using some techniques, asymptotic techniques, like Professor Gangoffer discovered for lattices, for beam lattices, or some, let's say, more naive approaches, and then use these 2D properties to find 3D effective. So it looks like harmonization squared. So we homogenized surface, and then we homogenized 3D. And so it's a typical example. It's not, again, changing conditions. Instead of zinc ore, perfect crystals we obtain zinc oxide nanoform, which looks like that. And okay, if it's foam, let me remind you that there are some cubic, for open cell forms, there are some models by Gent, Gibson and Ashby more popular, which just gives us some relations between foam stiffness and stiffness of materials, which depends on the porosity. And if we modify these formulas for nanoscale, we came to such kind of scaling law, which looks like that. So we use this scaling law by Wang, Karihalu, Duan, and we can say that, okay, our nanoform looks like that when we have some dependence on porosity with effects of size effects. And finally, we can say that our effective stiffness parameters looks like that. We have thickness, and you have this shear modulus, and so on, so on, so on. Okay, and another example is just array of fibers. In this case, two-dimensional constitutive equation should be transversally isotropic in some sense. And just some calculations, for example, in plane shear modulus looks like that. It depends on the number or density of these fibers and stiffness of these fibers. It's more interesting because here between these fibers there is also interaction forces of different nature, van der Waals, depending on what is electrostatic, van der Waals forces, which should be taken into account. Some references is conclusions shows, let me say that surface elasticity is so nice because it's quite similar in some sense to theory of shells, which is also very nice. It's also very nice and interesting mathematically. It's like geometrically interesting structure, and also you can capture some effects in more simple way, because if you see, for example, comparison with Stupin-Mindlin model, you should solve more complex equation in the bulk, and even in this simplified problem, these dispersion relations were obtained numerically, just because the matrices, and we have the matrices, and determinant of matrices must be 0. We should solve it numerically because equations became awkward at few pages in Maple and in Mathematica, so it is not so nice looking equations. And we have we can capture size effect, size effect, and other effects could be possible to describe. So, from my point of view, it's one of the interesting phenomena which can be used. And by the way, I missed, it's not my personal topic like nanocomposites. In this case, there are many results obtained for nanocomposites, for Gerten-Murdoch, for Steigman-Ogden models, and for others models. So it is just what was interest of mine. Okay, thank you for your attention. Grazie mille.
Thanks, Victor, for having speed up the presentation. There are some questions.
So, as far as I understand, you have a close correlation between the dispersion curve and the mu s or lambda s, the surface material parameters, right? Is it possible to find out an experiment which is giving us the dispersion curve and then maybe relate it to these mu s and lambda s, and then relate them for the second gradient material modeling that you did it? Do you see that as a possibility to find out?
It's quite good question. I guess it's possible, but I'm not experimenter. But the main idea was like that. We have just to characterize one model through another one. So now we have relations between one parameters and another parameter, saying, okay, if you have this, you can measure at least this, you can measure that. Okay, Professor Travalющin.
Just to understand a little bit the model, I would like to ask you about the immunity equations in which you have in a standard formulation with surface stresses, you have one equation, standard, and the contact equation of contact actions that are modified with additional terms, if I understood well.
Yes.
And I would like to ask, in the case of second gradient approach, in standard second gradient approaches, these contact equations are of the kind of surface equations depending, surface actions depending on the curvature, not only on the normal outward, normal to the plane, and or even if this is in the case of a tubing, for instance, theory, or even depending on line edges, edges contact actions like in the model of polyviruly and Fried and so on. But when you add surface stresses, this kind of contact actions are modified, are also modified as in the classical case, and then which way? I didn't...
Okay. Okay, in simplest case, for example, this is an example of modifying, let's say, boundary conditions given here. So we have, let's say, this is a normal derivative, is that just shear stresses. Shear stresses is given here, and here just a modification of this actions. So in the case of dynamics, you have this dynamic term. In the case, this is the second derivative with respect to tangent derivative, and this is just a tension. And here it comes from variational approach, just we consider least action principle, but it also could be derived as in the courses of technical mechanics for balance of forces and moments, just for the surface. Just must introduce some surface functions, surface stresses, and in general it looks, in the case of general statement, where is it? Let's say from. It looks here. So you have this divergence of surface stresses. If surface stresses, you have surface stresses of higher order. So inside of this begin surface hyperstresses. If you have some kind of, here we have strain gradient elasticity. You have more complex case because you have two boundary conditions instead of one vectorial, and also let's say more ingredients is present here. More ingredients will be present here. So you have just external forces and some additional surface actions presented here. It's okay?
And in the second gradient...
Unfortunately, for the moment, I cannot say, let's say, just come back. No, sorry. You're traveling.
With some kind of additional terms?
Yes.
Okay.
For strain gradient elasticity of such kind, you can see that we have motion equations looks more complicated. You have this higher order inertia terms. You have higher order stresses. You have hyperstresses here, which depends on the second gradients. You have something, and for boundary conditions for this antiplane motions looks like that. So you have quite, let's say, is not so complex.
Dispersion due to the presence of derivative of not the second order.
Here?
These terms and the other terms provide dispersion in
Yes.
Greek operation.
Yes. But here, unfortunately, we have more complex cases with more derivatives with respect to tangent direction.
Questions? Other questions? Okay.